for the past 8-9 months, on and off, we've been working on integrating LogUp-GKR. And yeah, we learned a lot of things that were not clear to us from the start. So the goal of this presentation is to try and convey this knowledge. So it was a little bit tricky to make it fit in 1 hour, not knowing very much of the background that people would have on the different topics. So how we tried to design the presentation is assume almost nothing and try to get to the end. So we'll start with more of the basics, and so that's why, like, if you have any questions, anything, feel free to ask. And if we don't finish, honestly, it doesn't matter. We can just like go straight to the conclusions towards the end. We'll try and make it, so that people, like, the goal is to convey these lessons. And I wrote this book on HackMD. The link is here. It's going to be probably like recorded, so I don't know. It's probably hard to type in, but if you just like look at my @Plaffer, everything that's in the presentation, or almost everything, is in this book. So yeah, so this presentation is more as a, okay, let's just talk it out, and any small detail, it's all in there. And yeah, feel free to reach out to either of the Miden team, and we'll be happy to help out. So that's so Bobbin will start with talking about the multi-set checks. Yeah, and basically most of the work here was done actually by Phil and Al over there. Myself participated very little bit, and the overall structures that we're going to go through this presentation will also have like some code to show you guys of how we've implemented it. There is like two versions of kind of like a dummy VMs that we've put together that show like when to use LogUp-GKR, when not to use it, and like in which settings it's applicable. So there will be like a coding portion to it, although you will not have to do any coding. We'll just show you the code and walk you through it. All right, so let's get started. A lot of what I will cover in this initial section is probably, looking at the audience, I think probably super familiar to everyone. So like, I'm not sure you'll see a lot of new stuff until we get further down, but I'll cover it anyway for the recording and maybe for a few people who are not familiar with it. But the first thing we want to start with is, the multi-set checks, and like, why do we use them? And like, we use them in Miden VM. They're used in other projects as well, very extensively. I would say multi-set checks is probably one of the biggest, if not the biggest, like innovations in the Start protocol since the original Start, because they allow you to do things that you were not able to do previously with like a basic Start protocol, and this is basically allows you to express non-local constraints. Without multi-set checks, constraints in Starks are fairly local. They're usually involving adjacent rows, or maybe a small set of adjacent rows, or sometimes you can jump, but in very regular offsets. With multi-set checks, it kind of allows you to kind of enforce constraints that like take some things from like this part of the trace against this part of the trace, and give you a lot of flexibility. A lot of things that we do in VMs, specifically in kind of Start-based VMs, would not be possible or would not be nearly as efficient without multi-set checks. So in Miden VM, we use multi-set checks for a few things. There is like a few things listed here. We use it for more than that, but we have like a stack-based machine. Miden VM is a stack machine, so like you want to have stack which is has very kind of like, you can put a lot of elements on it, so practically unlimited depth. This is what we use multi-set checks for. We can kind of emulate it using a lookup table. You want to do range checks. This is like a, almost a table stakes for any kind of useful VM where you need to check and make sure like some values are within a given range. 16-bit range checks is usually what we kind of care about, and then we can build other things from this. And again, you want to do a ton of those. And then we have some more esoteric instructions in Miden VM that allow you to do, like, say, Merkle path verification in a single instruction. So, like, from the main processor standpoint, there is one instruction, and then via multi-set check, you have a separate, we call them chiplets, or sometimes they're called coprocessors, where you can offload the verification of a Merkle path to a separate coprocessor, and it just does it from the kind of standpoint of the main VM. It's just a single instruction, but there is a whole other machinery running that allows you to do it separately. All right.
So we'll start with multi-set checks, and then we'll build up to LogUp, and then from LogUp we'll go to LogUp-GKR. So I'll do the easy part, which is just the multi-set checks, and then Phil will handle the more complicated stuff. So multi-set checks, again, probably super familiar to everyone here, but we have, we want to make sure two sets of values, or in our case usually field elements, are equivalent. And in this case we say, what matters is that if the two sets contain the same set of elements, it doesn't matter in which order. So if they contain the same set of elements, they're considered to be equal. If one set is missing one element, they're obviously not equal. Order doesn't matter. Repetitions do matter. So like if you have 2 3s in one case and only 1 3 in the other case, those are not equal sets. And the core idea here is that we will represent kind of these sets as polynomials. So you basically, as roots, you take the values that you want to have in a multi-set check, you set it as a root of polynomial, and then you want to check if the polynomials are equal, and the way you do it is evaluate at random points. So you basically take them at random point, you compare if evaluations of the two polynomials at random point are equal, and that's how you figure it out. In Miden VM, like this is a little bit of an eye chart, and I'm not going to go into this, but this is like the layout of the trace of Miden VM. And you can see like there are different parts to it. Like there is, for example, the main processor is here, there is a decoder here, and then there is like a bunch of chiplets and a range checker on the right side, and there's like some system trace here. And you may want to have some things that you put into, like, let's say, one of the sets, and they can come from different parts of the trace. For example, an example of this could be, although this is not the correct example for this, but let's say you want to do a range check. So you'll do a bunch of range checks. Like you say, okay, I'm going to range check a bunch of values here. And then let's say you want to have the other part. And again, range check is probably not the best example, but you can say, the left-hand side of the multi-set check is going to be these green boxes. They can be contributed from any part of the trace, and the right-hand side is going to be these blue boxes, and then they also can be contributed from another part of the trace. And we want to make sure these sets are equal. So kind of this is a more general form of describing it, because every row can contribute multiple values to a multi-set check, so to say. There is a constraint on how many rows per value, or how many values per row you can contribute, and this constraint is usually run into the degree bound. So like the more things you want to, at least in this setting, when we use multiplications, you run into the constraint where you can add a lot of, like, you can add some values to the set that you want a multi-set check against, but let's say if you put 8, your degree of your constraint may need to be 8, unless you introduce additional columns to kind of like reduce the degrees and things like that. But here you do this multiplications to add more values from the same row. And if you have k elements in the row that you want to add, your degree could go up to 8 or up to k unless you reduce this. One of the benefits of LogUp-GKR is that this actually is no longer the case. You can add more things per row and you don't have the same degree constraint. And then the way we express it in Starks is by using this running product column. So let's say we have these two sets, and A and B, and this is a simplified view where like the column is entirely one column has the A values and the other column has the B values. And what we want to do is we want to have this running product column where whenever we have something on the left-hand side of the multi-set check, it gets multiplied into the column. And whenever we want to have something in the B side of the multi-set check, we divide it out of that column. And so, this column progresses, it starts at 1 because there is nothing that we compare against, and then as we go row by row, we either multiply or divide, multiply values in or divide values out of that running product column. And if the sets are equal, like by the virtue of this kind of the formulas that you can see here on the right-hand side, you should end up with 1 at the end. This is a very kind of standard way of doing this. There are other variations on this where, for example, you can start not with 1 but with some other value, and then you run through the same product kind of computation running product column, and then you may kind of initialize your set in one way, or you may end up with not 1. And this is useful in other ways, like you can basically say inputs and outputs of this table. You can kind of prime them or use some outputs out of them to say, okay, like it didn't actually was equal, but I can tell you exactly which parts were not equal, and that is useful in other ways. Yeah. So there is one problem with this, though, is that as soon as we introduce randomness, like our trace usually base field elements, so randomness and adds a little bit of complexity here. So what we need to do is that we actually have an auxiliary trace, is what we call, which is actually an extension field, and this really matters only if you're in a small field, which most Tark nowadays tend to be in the smaller fields. If you're in a large field, extension, like you still have auxiliary trace, but it could be in the same field, but let's say 64 or 32-bit base field, you actually need a larger value for randomness. 64 bits is not enough for randomness. 32 bits is not also enough, so you usually want to be at like 128 bits or maybe even higher for a good level of security. And so the flow is usually the prover commits to the values that they want to multi-set check in the main trace. Then the verifier sends the randomness. Usually this is done via Fiat-Shamir kind of transformation practice, where we go from interactive to non-interactive protocol, but you basically get this random value alpha. This random value alpha then is kind of used to compute this auxiliary column, which gets added to the auxiliary trace, and we get our multi-set checks. Now, and then we need to impose the boundary conditions on this auxiliary column, like if we want one to start with one and end with one, if we want the sets to be completely equal, or again, as I mentioned, you can actually initialize or like put different boundary conditions on it. Now, the other useful thing would be is to be able to specify multiplicities for values. This is a good example of this is a range check. Sometimes the same value may get checked many times, and instead of like repeating it many times in the trace, you may want to say, okay, I've seen this value like 5 times. I don't need to repeat it. I don't need it to occupy 5 separate cells. I want it to be kind of like still very efficient, expressed in one cell. So basically what we get is like, we would want to say, okay, this is the value that I'm going to put in the set to multi-set check against, but I also want to specify how many times it needs to go into that set. So you would say, okay, some values go 0 times, some values go 1 time, some values go 5 and 100 and so on and so forth. So this is very useful, again, when you have let's say a relatively short trace, but like every row can contribute multiple range checks as an example. And instead of like growing the length of the trace, you can just say, okay, this value was range checked like 100 times. And you don't need to like add extra 100 rows to your trace for that. So this would be a very cool thing to have, and here you can see like this is a general form expression of how to do it. The problem, of course, here is that these are no longer the constraints are no longer polynomials. Like if in this most general form, like if you try to apply this multiplicity this way, you don't get like the same polynomial constraints. So you kind of like are in a difficult spot. You can actually do multiplicities, like in a very early version of Miden VM, we did like limited version of multiplicities where you could specify like a limited set of multiplicities. So it would be like, okay, I'm going to add either 0, 1, 2, 4, or like 8. And this would be your only multiplicity choices. And in this case, you can actually write constraints where you can say, okay, this value is going to be repeated 4 times, or this value is going to be repeated 2 times. The constraints are not as nice, but it is doable. But there is actually like much nicer construction, and this is LogUp. And here is where I'll hand it off to Phil. Yes?
If you got 2 slides, how can you have multiplicity value of 0? How do you know that A3 is going to be multiplicity 0?
How do you know ahead of time, or?
Yes.
Usually you don't necessarily know ahead of time. So like in the example of a range check, like the way you would do a range check is that, and let's say it's a 16-bit range check. You would write all the values, like the simplest way is you would initialize all the values from 0 to 2 to the 16 minus 1. And And you would basically fill in those values, like whatever things you didn't use, like the prover would later go and like say, okay, this value was never range checked, so I'll put 0 in against it. So it's not something that you would know ahead of time. It's kind of like after the program is done, you kind of usually fill in those columns. So you keep kind of a running count of how many times a given range check was used. And then at the end of trace generation, you would go and fill in the multiplicity column based on that. Yeah. We actually do, in Miden VM, instead of like listing all range checks, like all possible range check values like from 0 to 2 to the 16, because we want traces to be usually sometimes smaller than 2 to the 16. We don't want to list all possible values if they're not used. So we actually skip some values, like, and we usually go in like powers of 3, I think, where we would start with like 0, and then if like, let's say the value between 0 and 8 was never checked, we'll like insert it like a value 8, and so on and so forth. So your trace could be as small as 256 rows. I think we can, like the smallest trace Miden VM can have, because the values of the range checks that were never used are never actually added to the trace. We kind of do the skipping thing. All right. Now we'll go to LogUp, which is a much more exciting way to do multi-set checks.
Yeah, right. So where we left off is how do we introduce multiplicities and actually able to prove them properly. So we'll start by doing it in the Stark context, which is a very similar construction to the running product column, and what this leads to is, okay, we're going to want to prove this with GKR instead of a Stark. So we'll start first with the Stark. Right. So as a reminder, now I'll just go into the derivation of LogUp to just get an intuition for where it comes from, where this equation, we're going to transform this equation. So we start with our multi-set check equation that has these powers that we're trying to get rid of. So first we apply the log to both sides. This is field elements, and log is typically over the real numbers. Paper goes into the formal treatment of this, but for now we're just going to use this as an intuition. So we apply log on both sides. We apply the log rule where multiplications in the inputs are transformed into addition, and also this is how we got rid of our exponent. We apply the log rule of x to the y becomes y times log of x. So here our MA and our MB are now multiplying the log. And then the final step is to derive both sides. So we apply ddx. A bit of an abuse of a notation here. We're doing it over alpha, and alpha was our random value. It was just to keep the slides similar. Really, this is a polynomial over x, and we're doing the derivative over x. So really substitute alpha with x in your mind. So really, we're deriving x. So when you apply, you move it in the sum and all that. This is ultimately the equation for LogUp. So, two things to remember is this is exactly equivalent to, this will check the same thing as the version that was doing a product. And we succeeded at no longer having exponents. Like that's the whole reason why we did this. So here, this is exactly the same equation as this slide, except that I just moved everything on the left-hand side by subtracting both sides, subtracting the right-hand side to get everything on the left-hand side. And so we're going to do a running sum column. It's very similar. Instead of products, we get sums. So we're just going to do a very similar thing. So our running sum column is going to start with 0. At every row, we add the set A, and we add all elements from the set A and remove all elements from the set B. So in this case, set A at row 1 has A1, and so we do 1 over alpha minus A1, and then we remove what's in set B, and so 1 over alpha minus A2. And then we do this at every row, where we take the previous value, of the P column. So it's a running sum. So you take whatever was there before, you add in the new stuff, and you add in the new A's, and you remove the new B's. And at the end, if your multi-set check is indeed, if the two multi-sets are indeed equal, you're going to get a 0 at the very end. And as Bobbin mentioned, you can actually make it not 0, but for the purpose of this presentation, it's just going to be 0. We want equality of multi-sets. So if we look at the constraints for this running sum column, we have P at I plus 1, so the running sum at the next row needs to be equal to the previous row, so whatever was there, plus add in all the A's and remove all the B's. This is not a polynomial yet because we have these fractions, but by multiplying out the denominators, we get a polynomial. So don't worry too much about exactly the equations here. Like it's a lot to take in at once. The only take-home message is we're able to make actual constraints that have a field element as a multiplicity. So we're able to use multiplicities freely using LogUp. So now we're going to go into how to do this with GKR, which is what LogUp-GKR is, and why we're all here. There's one issue that we're going to look at right now that's going to be super important later, and Bobbin already alluded to it, is the degree of the constraints. Those are going to be a problem or something to deal with, and maybe even something that motivates the use of LogUp-GKR. So if you look here, we have degree 3 or more, because our constraints are over all the variables in the current row and the next row, so all the columns in the current row and the next row. And so here we have P at I, AI0 and BI0. Actually, AI0 and BI0 are, in general, polynomials of columns, so they could have their own degree. They could be degree 5 and degree 6. But the minimum is their degree 1, where they're exactly one column. So the minimum degree of this expression is 3. And it goes up as you don't, if you don't commit to everything, basically, and you do polynomials of columns, then this degree goes up. And VMs typically have a limit on the degree of constraints. In mine, currently, they're at 9, and it's pretty high. Many VMs use 3, and so you're basically not allowed to do use any polynomials of columns. You need to use directly the column. So if you need these expressions, you need to commit to new columns. You need to create new columns just to make that work effectively. And that's extra work for the prover. So then, so let's go into LogUp-GKR. We'll come back to this point. So GKR for LogUp. So GKR is an older protocol, and it was adapted to make it work for LogUp. We're not going to discuss the original version. We'll just talk about the modified GKR, but in spirit, they're the same. So GKR is a protocol to prove the correct evaluation of a layered circuit. So we have a circuit here. We'll go into the details of what's in there. But just in general, you have a circuit, and you want the prover to evaluate it, and the verifier to succinctly be able to check that the prover indeed did this correctly. This is all that GKR does, or all that it does. So we're going to design a circuit for LogUp, and it's going to encode effectively this equation, that's the LogUp equation we've seen. We're going to design a circuit that computes this. So in the first row, we're going to encode the entire sum. So really here, A over B and C over D, this is the flattened version of what you see on the double sum you see on the bottom. So it is for every row, there's K elements, you flatten them all out, and the input layer of that circuit is going to contain all of these fractions. And then what we do is when we go up a layer, so with every new layer, we reduce the number of fractions by half by combining just how we do it in high school math, combining fractions with a common denominator. And we do this until we have one fraction. Actually, for technical reasons, we'll stop at 2, but conceptually we'll go all the way to a single fraction that is equal to, like at every layer sums, if you were to sum the fractions, they all sum to 0 in our case. In general, it's some number, but really we'll just talk about 0. So what does that look like in a circuit? We'll have one node per fraction, and each node is going to contain 2 numbers, the numerator and the denominator. And a sum is going to be defined as, a sum over these pairs is going to be defined as just what you do with fractions. So AD plus CB for the numerator, and then B times D for the denominator. And yeah, in the paper they call it the projective representation, whatever. It's like it's pairs and you think of them as fractions. Right, so then I guess just conceptually we have everything for LogUp-GKR, is in that instead of doing this running some column, the provers instead is going to build this circuit, use GKR to prove that it was done correctly, and then we will have proven our LogUp relation. But now we'll dig a bit more, because there's actually a lot that goes into it. I will not go into all the details of GKR. I think it'd be pointless. There's already a bunch of information here. We'll just go into what you sort of need to know for this presentation. Feel free to ask questions. It's a little tricky to go into enough detail, but not too much. So we'll just go into the basics. So what is sum check? I won't go into all the details. All that's really important for this presentation is, first it's multivariate. And so G is over, M, well in this case, M variables. And what you prove with a sum check is this G, it's a polynomial. It's defined over F being your field F to the M field elements, but you evaluate G over the Boolean hypercube, or really all bit combinations of M bits. So 0, 0, 0, 0, 0, 0, 1, all the way to 1, 1, 1, 1. You evaluate G at all these points, you sum them up, and the sum check is a protocol to prove this value, that this value was computed correctly. Two things that are important is, obviously there's polynomials, and therefore you have evaluations at random points. In the case of sum check, we're going to be sampling M random points during the course of the protocol, and the verifier at the very end needs to evaluate G only once and at this one random point. This will, and we'll come back to this, but this is like the crux of sum check. The second concept of 2f2 that's necessary is effectively how do we do interpolation in the multivariate context. Lagrange interpolation in the univariate context most people are familiar with. I didn't assume that everyone had done it in the multivariate context, so we'll just go a bit more quickly into what that looks like. But it's you can think of it exactly as the same, as you have, well, we'll get to it. So first you have the equal function, and it's equal over m x's and m r's, and so it's xi ri plus 1 minus xi, 1 minus ri. What is this? It effectively outputs, when you put bits in, it'll evaluate to 0 if the bits are not equal, and it'll evaluate to 1 when the bits are equal. You can actually plug the values in and check for yourself, but that's how it's designed. But again, ek is a polynomial. It is not just defined over the Boolean hypercube, but it's really designed to be to have this effect. I guess one thing to note is that the degree in all xi's and in all ri's is 1. If you stare at it for long enough, you'll notice that this is the case. You never have xi squared or whatever. So the multilinear extension, or Lagrange interpolation in the multivariate case, is if you have your f function, which is defined over bits, Boolean hypercube, the domain is only bits, and you want to fit a polynomial. This is the equation. It's maybe a bit scary, but honestly, it's quite intuitive. We sum over all the possible bit patterns. We check if it's equal. When it's equal, we output 1. If it's not equal, we output 0, and times f at that bit value. And so you can see that if r is one of the bit values, let's say all zeros, ec will evaluate, like the equal function is going to evaluate to 1 only for 0, and all the other bit values, it's going to output 0. So we're going to zero out all the other values. So we can see that f tilde, or the multilinear extension, does indeed interpolate f. And the degree is 1 because it is it's in R. And as we talked before, the ec function is multilinear. So yeah, by I guess function composition, not even composition, the multilinear, the f tilde is also degree 1 in all the variables. Okay, so two things, sum check and multilinear extension. We're now going to come back to GKR. We're going to be building some functions over the Boolean hypercube, and then we're going to be taking the multilinear extension, and then we're going to be doing sum check. So this is why we did all this before. So if we recall, so maybe if I go back just to give context, this was our circuit, and we're just going to zoom in on P1, Q1, so the middle layer. So we have the middle layer here. We're going to build two functions over the Boolean hypercube. P is going to be all the numerators, and Q is going to be all the denominators. So, and you can think of it as, it's the bit decomposition of the index. So P at the bit decomposition of 1, for example, so 1, 0, is therefore the second one, EH plus DF, the second numerator. P at 0, 0 is AD plus CB, and yeah, so P really encodes all the numerators, and Q encodes all the denominators. And we do that for every layer. So if you remember, just by circuit construction, we can then define, every layer is defined in terms of its previous one. I mean, just to really make that point clear, here we had fractions. Every new layer is taken from the fractions from the previous one, and you merge them into a new one, into this new layer. So now, all that we've done so far is we define the P and the Q functions. So we're now just going to apply what we did from before, but just in that new language. So P at I, so at layer, let's say 1, is P at 2. And then I think I have, yeah. And it is basically, in the next layer, it's the numerator times the denominator plus the numerator times the denominator, like left, right. This is a bit hard to say. If X is your bit, if X is in red here at layer 1, so 0, 0, 0, 1, 1, 0, and 1, 1, you can see that the children start with, if I'm a child of 0, 0, my most significant bits are going to be 0, 0. If my parent is 0, 1, my most significant bits are going to be 0, 1. So this kind of explained why if x is basically whatever is in the input layer, sorry, not the input layer, the layer above, you can see that on the next layer we reuse that x, like here, we reuse that x because of that fact, and we either do 0 for the left or 1 for the right. And so I guess it's a little bit much to take in, but it's just rewriting exactly what we had before, but in this new language, and reusing this circuit structure where your parents have the same bits. Yeah. So now we have functions over the Boolean hypercube. We're going to take the multilinear extension to make polynomials out of them. We're just going to fit a polynomial over P and over Q. So all I'm doing here, I probably could have written this more simply, but all this is the multilinear function for P. So we sum over all possible x's, we pass into x, and then we pass in the definition of P. And same for Q. I realize that it's a lot on one slide, but really there's not that much. If all that you get from this slide is we're building polynomials out of these functions, that's all there is. Yes, yes.
But like when we go to this extension, like the EQ function is well defined only on the Boolean hypercube.
Ah, good question. So the question was, when we said that the EQ function was only over the Boolean hypercube, so how is this well defined when we're in other field elements that are not 0 or 1? So the EQ function, and maybe I was not as clear earlier, is actually defined, here, let's go back to the definition. Yeah. It is defined over not just the Boolean hypercube. Like if you look at the equation on the right, this holds over all field elements. When you put in zeros and ones, you get these properties, but it is actually defined everywhere. For all x's and all r's. So
but you get like the semantics of equality for all the two elements, or defining it, but I can compute it, but like the output value is not.
Exactly, it's going to be a big number. Yeah.
Okay.
Yeah. So this is exactly. Thank you for that's. I should have made this more clear. The EQ function is a polynomial that has these properties over the Boolean hypercube, but really it's a polynomial. So if we go back to what we had, big expression, honestly I should have written it a bit simpler just because it's a lot to take in, and actually there's not that much. We have like two sumcheck instances here. What was sumcheck? It was summing over Boolean hypercube of some polynomial, and this is exactly what we have. We sum over all Boolean hypercubes of x, and we have the polynomial over x. And x hat in this sumcheck is considered to be fixed. So the only variable when you're thinking in sumcheck terms is over x, and x hat is fixed. What I'm trying to get at with this slide is we did all of this so that GKR can use sumchecks. In the next slide. And please ask questions. I'm happy to spend, yeah.
Yeah, it's basically those two polynomials, which are expressed as sums over Boolean hypercube, basically are, they're setting up a sum check where you can do a sum check for each layer in order to get from your large expression down to fully reduced.
Exactly.
Okay.
Yes, that's precisely it. And that was like what I was trying to get with exactly this side.
So
no, man, it's perfect. So, okay, so what he said. So we have two sumchecks. There's a standard trick when you have like two instances, you can just take a random linear combination and just solve one problem of the combined, like the batched or the combined problem. So here on the left we have pi at x plus lambda qi at x. So that lambda is random, so we're looking at a random linear combination. And then when you actually work it out with the sums and all that, you get this on the right. You get the ec function times the p plus lambda the q. This is like copy paste of p plus lambda and then copy paste of q. So this is our sum check problem that we run at every layer. I will not go into the details of exactly how we do this reduction, but as was said, is the whole point is, and again, more details in the HackMD, but like for the purposes of this talk, we have a sum check that is going to reduce to another layer, to the claim for the next layer, which we're going to use sum check again to reduce to another sum check problem all the way down to the input layer. Right. So also just to try and give an intuition is we're never able to complete the sum check at every layer. It is never done because if you remember from sum check, the verifier has to evaluate G, which is like whatever's inside that sum, at that random point. But G, in this case, is a bunch of circuit nodes, and the verifier doesn't have the circuit nodes. So what we do is the prover sends in the values as claims. It's like, I'll fill in whatever you don't have, and then in the next layer we'll prove it recursively. So the intuition is this, and so by reducing to, we mean prover sends whatever values are needed for the untrusted values that the verifier needs to complete this round sum check, but then we're left with, okay, well, these values I don't trust. We're able to combine them into this, what's at the bottom of the slide, pi plus 1 at this row, and it's just some new random variable, random value, and then we're able to do this recursively until the end. So the only mental model to have, if you've worked with GKR, this makes sense. If you didn't, probably not so much. Like it requires a bit more thinking. At least I did. So maybe the only thing to really try and to fill is, if we go over all that we talked about is, we have this layer. Or rather every layer we fill in these two polynomials, P and Q, for every layer. And then the verifier says, okay, evaluate these at a random value. We're going to do this with sum check. At the end, I'm not going to be able to complete the sum check, so you'll send me some values so I can do that. But I don't trust those. So I'll reduce this for a statement, and it's all nice. I reduced it to a statement for the next layer. So to prove these values, it is exactly the same as proving the next layer, all the way down to the input layer. That's the intuition to have of how this process works. Right, so, okay, so I guess that's what I just said. So I'm going to first send, but maybe we can also just do it a bit slowly. So we have our circuit. How do we prove LogUp in GKR? That's sort of the last slide about this. The prover sends the top layer. And as we said, we have two fractions left. So it's P0 at 0 and at 1, and Q0, or rather Q for that layer at 0 and at 1. The verifier checks that if you interpret these as fractions, does it sum to what we said, S, think of it as 0. It can be something else, but think of it as 0. So is your output layer correct? And obviously you check that the denominators are not 0 before you do that. If the verifier agrees, like, okay, perfect, your output layer is good. Now I'm going to need you to prove that it's effectively related to all the way down to the input layer, that this is not just some random numbers you sent me. So then we sample at like an evaluation point for Q and P and Q. This is, okay, prove this to me. At every layer, we're going to run sum check at this random point, which is, it's this polynomial check of I'm going to sample at a random point. If it's good, if it checks out, we're happy. And then for the final layer, in this slide, we're going to assume the verifier has the final layer. We're going to correct that in the next slides, but we're just going to say, okay, I've reduced it to this final layer. I will then evaluate the final layer, make sure that it all checks out, and if it does, yeah, we're done. So, any questions up to now? There's been a few, but I can. Okay, so what we have until now is we were able to prove everything all the way up to the input layer. And the input layer could almost be a talk in itself, in and of itself, because there's actually a lot that goes in there. It was by far the hardest to understand for me.
I have a question. Like,
yes.
How the verifier evaluates the biggest layer below directly?
Yeah, good question. This is the topic of this section. Yeah, and so gluing LogUp-GKR to Starks, like that's like a big challenge. So what we'll go into is really understanding what needs to be done, and we'll give some details. We won't give them all. Happy to dive wherever is needed.
We also have like 15 minutes left.
Okay, so that's why. All right, I'll do this in about 5 minutes. We have a few things to run at the end. I'll skip this slide then. Okay, so as an example, we'll just remind ourselves, we've talked about this earlier, of how what is the input layer, right? It is, as a simplification, elements from our trace. Bobbin talked about it for a bit. So on the left-hand side here, we have our trace. And as a simplification, we'll say that the entire first column is all the MA values. The F2 is all the multiset A. And then same for F3 and F4, but for B. So you'll have the multiplicity for B, and then the B multiset. And when you lay out the LogUp equation at the bottom, you have, yeah, I mean, we've been over this. This is all stuff we've talked about. And again, that's just a reminder, this is how they're laid out. The big challenge for the input layer, given that there's not so much time left, we'll just go more with the intuition of the work that needs to be done, is there needs to be a protocol to prove that these values actually come from the trace without ever showing the trace, because in a Stark, the trace is never sent to the verifier. So how do you do that? There's going to be a boundary between the GKR and Starks, and that boundary is going to be the multilinear. So if you take each, where F is the column, so we have M columns in this case, GKR is going to reduce to a statement about the multilinear extension, or fitting the Fi columns at this random point. It's going to be able to prove all the way up to that. And then the Stark is going to take it from there and it's going to say, okay, this is what's left to be proven from this entire circuit evaluation. This is my job now to prove in Starks. One thing to notice is that Starks don't speak the multivariate language. We typically speak in univariate, or we speak in univariate language. So this multilinear extension is not a thing in Starks. So we need to do this somehow. Honestly, I won't even go into that. Like, just to give a final intuition is we're basically going to be proving this with two columns. We're going to have one column that is the evaluation of EK that we've talked about, and then another column that puts everything together. Like, I'd like to spend more time here. I think we can maybe run some of go to the conclusions. I think the conclusions of when is GKR good may be more interesting than the specifics of this. Happy to go into it though if there are questions.
That should be a row inside the FJ.
No, so EK, we're summing over all x's. EK is taking that row equal, but then you pass in the x. So like over bits, when row is equal to 0, 1, or sorry, bits. Does that make sense? Or I did not explain how to construct the sum, so
No, fj takes one variable, and x is a vector.
Mm-hmm.
So, and row is one variable.
No, sorry, row is a vector as well. Row is as wide as x is, but in field elements instead of honestly, I apologize. That was not properly explained. Yeah, that's a. All right, so that's like, when is it worth it? That's the part that was very much not clear to us, and it is now. So if we try and like take a step back from everything we did, we're comparing when we're proving LogUp either in Starks or in GKR. In Starks, we often have to add a bunch of, like when our expression gets very big, as we talked about, we need to add helper columns. And maybe it would help to just go back to this slide, and we'll just talk from there. The big issue, so this slide at the bottom. The big issue with the proving it in Starks is you probably have to add a bunch of columns for these intermediary expressions that would blow up your degree to very high if you didn't. So then all these columns in the Stark protocol, they're all being hashed. So you can think of, when I'm proving LogUp with Starks, I have a bunch of extra columns that are for the LogUp only. And the question is it worth it to remove this work? So we're going to get rid of all these columns and then add the overhead of all this, the protocol we talked about for GKR has a cost. So which cost is smallest is the question we have to ask. And there's like 3 parameters we'll focus on is how fast is your hash function? So if hashing these columns is extremely expensive, then getting rid of a bunch of columns to hash is going to be good. If your hash function is extremely fast, then it's all, if you think of it as free, then you don't care to add a bunch of columns. That's one consideration. Second consideration, which goes down to how many columns you have, is how many fractions, like how big is that k here? How many fractions do you have in your bus or in your multi-set check? If every row can add 1,000 elements, you're going to need way more columns just to fit these intermediary values that like many columns. That's going to be a lot of work for the prover. If you can get rid of all that work and put it in GKR instead, it might be good. So like just another consideration is how many things are you putting in that bus? And then the final one, I think we want to talk about the extension field. We might skip that.
The degree is the last one.
Yeah. Right. So the degree is the last one. So, well, I guess it was the second one. So we've alluded to that already. So if the degree of your constraints is low, you need way more helper columns. The higher you go, the less columns. So it's always in this question of how many columns am I adding and how expensive is that versus the overhead that I get with GKR. Only benchmarks can tell you that at the end of the day. It's many variables. So that's what we're going to do. So I'm not going to show code because I don't think we have time. I will only run. So we're going to vary which hash function. We're going to use a slow hash function and a fast hash function. And then we're going to be increasing the size of the bus. So we're going to look at slow hash function and then add more things to that bus so that we need to increase the number of columns by a lot. And we'll look at it, okay, what happens when we prove that in Starks and what happens when we prove that in GKR. So on the left-hand side, is that big enough? Well, honestly, I can just read it out. So this is, on the left-hand side is going to be proving with Starks. On the right-hand side is going to be proving with LogUp-GKR. So this has 16 fractions per row. So the k here would be 16. And so we've proved it in 4 seconds, like 4.4 seconds. If we do the same thing with LogUp-GKR, again, this is using a slow hash function. So we expect LogUp-GKR to be good at some point. 4.5 seconds. So at 16 elements in that bus, they're roughly equal. If we go to 32, so now we're adding even more things in that bus, so we're adding even more helper columns, so the slow hash function is starting to be expensive. 6.5 seconds, if we do the same thing with LogUp-GKR, hopefully LogUp-GKR is better in that case. And 5.9, 6.5, yeah, so it's 500 milliseconds, 600 milliseconds faster. And these are not proper benchmarks. We should use proper tooling. This is just to show. Okay, so what we've seen right here is that at 16, the size of the bus, 16 roughly equal. If you add in more, GKR started to be useful. And real numbers, I think in Miden VM we have about 60, 70 the fractions in our bus, so it's definitely worth it using RPO, using this slow hash function. We're going to do the same thing with a fast hash function, so Blake 3. So Blake 3 will do 16, and the punchline is that Blake 3 will never, LogUp-GKR will never be better when we use Blake 3, unfortunately. So Blake 3, we did it with 16. Right, so we have 500 milliseconds, so 0.5 seconds versus 1 second. And if we go all the way to the bigger one, which is 168, 68. If we put 168 things per row in our bus, so many helper columns, we have 4.5 seconds in the RPO case. In the LogUp case, no GKR. And in the LogUp-GKR case, 6 seconds versus 4.5. So LogUp-GKR is still slower. Okay, a couple of things about that. So slow hash function was better with a sizable bus. Fast hash function, at least this current implementation, LogUp-GKR is never faster. Al has worked on a bunch of awesome optimizations. That is not what I'm running right now. We get closer, but it's still not quite there yet. So for the Miden rollup specifically, we're going to use a slow hash function. So it would be preferable to use LogUp-GKR. But maybe we don't want to do it for the entire VM because people might want to use it and use a fast hash function, in which case LogUp-GKR would slow them down. So yeah, I guess like the big takeaway from all of this is LogUp-GKR is not always good, and the main framework that we have is the cost of all these helper columns versus the overhead that GKR gives you. I'll leave it at that.
Yeah, I think like the takeaway is that in our current implementation of Miden VM, where we have relatively like.
You want to talk over in the mic?
Yeah. We have like relatively few buses. Like we don't have a ton of bus columns, and we have high degree. I think where we ended up is like using RPO, we kind of break even in terms of LogUp-GKR and non-LogUp-GKR approach. If we use Blake 3 as a hash function, we are like twice as slow, I think. I think that's what we've seen. Now, we do think there are a few ways we can improve. Like one of the ways, like is if we went to a lower degree kind of instantiation of Miden VM, where right now our degree bound is 9, and if we were to go to degree 3, that would like automatically mean that we need more intermediate columns. And in that case, like in a RPO context, like it's no brainer. We should be using LogUp-GKR. There is no reason not to use it. In a Blake context, I still think it's an open question. I think Al, you try to get it close. I don't know if it will break even or will be slightly better. We are not quite there yet to say for sure, but even with Blake, we might be able to get to a point where it's kind of like at parity. But it is still an open question whether we will get there. But yeah, that's kind of the main thing. I think there are a few other things to consider about LogUp-GKR, because one of the things that was not obvious to me, like in a LogUp context, in the beginning, like you can actually place boundary constraints against the starting value and the ending value of this columns, of the running sum columns. In LogUp-GKR, you cannot do that. You kind of can have like this single value for the entire sum, but you're not able to do like boundary against the beginning and the end. And in some contexts it doesn't matter, but in some contexts it does matter, where you, like if you want to link through those things externally, it may create a little bit of challenges. So like, I think overall like LogUp-GKR work is super cool, and like we learned a ton. Whether we'll use it immediately in Miden VM is probably, we still need to figure out if there is usability, kind of like immediate usefulness to this. But I think in the long run, there is clearly something that we will use as we kind of reduce the degree and do other things. So like, it's been a very interesting like learning experience, I would say. Yes?
In the demo, you discussed only the proving time aspect, but it's also there was verification time and proof size. And at least in the last two examples, it was clear win for the stars rather than the GKR. Didn't notice it for the first examples. Does it ever win in verification time and proof size?
Yeah, that's a good question. Al, do you have a better intuition as to verification? So the question was, we've only focused about proving time. What about verification time and proof size?
I think verification time should still be even competitive for LogUp-GKR, because you are not doing a lot of hashes, right? And you are doing more algebraic. Like the verifier basically just evaluates polynomials for the subject verifier. So it's very hard to beat that in a sense compared to hash and loops. Like if you have like very wide traces, which means that you have to hash like more columns in absolute traces. So from that point only maybe, but the proof size is probably worse. Probably worse.
I think most of your hashes you don't really do for all of the columns. Most of your hashes will be for
sorry to interrupt, but we are running quite a lot over. We have a break.
Yeah.
So maybe continue the discussions outside. There's a nice little hangout there.
Yeah, we're happy to like step outside and talk through those things.
Thank you very much.
Thank you.